All right, let's get right into it. We're looking at one of the absolute highest stakes, high pressure operations in the entire oil and gas industry, cementing a well. You're quite literally racing against time and physics here. You're about to pump cement down a casing, and the tool that controls this whole unrepeatable operation is our topic for today's explainer, the cementing head. I want to establish the golden rule of this explainer right off the bat. Cement sets whether or not you got the job, right? It really is that simple. This makes cementing one of the very few rig operations where a mistake simply cannot be undone. There's no control Z here. You get exactly one shot to place this perfectly, and if you mess it up, well, you're looking at a catastrophic failure. So think about the environment inside that pipe. The big question is, how do you separate three different fluids traveling together? You've got your drilling mud ahead, displacement fluid behind, and your critical cement sandwiched right in the middle. If they mix, that cement turns into this soft, muddy gray smear that's never going to seal anything. The job would be ruined before it even really starts. They absolutely must stay separated. And keep in mind, we aren't just moving this fluid a few feet. We're attempting to pump this cement perfectly down 13,000 feet of casing. That's over 2 miles straight down into the earth, entirely in the dark. Which brings us to the actual control point for this massive undertaking. Sitting right on top of the casing string is the cementing head. As you can tell, it's a massive, heavy, flanged steel fitting. This essentially serves as the surface launcher for our entire operation. It's got an inlet for the cement pump, but its main job is to hold and release what we call wiper plugs into the flow at exactly the right moments. If you want a great analogy, think of a drive-through bank's pneumatic tube system. You know how that plastic capsule seals perfectly against the tube walls so the air behind it pushes it cleanly along? That's exactly what wiper plugs do. They're basically traveling seals. But they actually pull double duty. As they travel, they aggressively scrape the mud film off the casing wall because, as we know, cement just cannot bond to a dirty, mud-coated pipe. The mechanics of this are just genuinely elegant. First, you drop the bottom plug ahead of the cement. It's hollow, and it has a ruptured disc inside. It wipes the mud on the way down, lands, and then the pressure bursts that disc so the liquid cement can flow right through it. Then, right behind the cement, you drop the top plug. Now, this one is solid. When it lands on top of the bottom plug, it stops the flow dead. Back on the surface, your pressure gauge sharply spikes. We call that spike the bump, and it's your ultimate confirmation that the cement is exactly where it needs to be. Once this is all rigged up, everybody on the job, the cementer, the driller, the company rep, they're all watching this sequence together like a rocket launch countdown. Drop the bottom plug, pump the cement. Drop the top plug, wait for the bump, check your floats. This strict chronological precision is absolutely critical, mostly because the clock is ticking on that curing cement. But, man, here is the truly terrifying part of the job. How do we actually know when to stop pumping if we can't see what's happening miles underground? You're standing there waiting for that top plug to bump, but what if something goes wrong? That brings us to the concept of displacement volume. This is the casing's internal capacity, which is calculated and independently double-checked before the job even begins. It dictates exactly how much fluid it takes to push that top plug from the surface all the way down to the bottom. Relying on this exact calculation prevents over-displacement, because if you pump past this calculated volume, you're going to push the cement entirely out the bottom of your casing, an area known as the shoe, leaving you with a wet, completely uncemented hole. Let me throw a scenario at you. You've pumped the exact calculated volume, but you didn't feel the plug bump. Do you keep pumping? Absolutely not. You stop immediately. This is a real high-stress decision that people get wrong under pressure. Look, if it didn't bump, a plug might have failed to release, or maybe there's a leak. If you chase the bump by pumping just one more barrel, you're going to over-displace and destroy the bottom of the job. You have to trust your mouth over your instincts. Okay, so let's say the math worked perfectly. Everything's great, right? Well, once our cement makes it to the bottom, we face a brand new problem. Physics instantly tries to undo all of our hard work. See, the cement in the annulus, that empty space outside the pipe, is way heavier than the displacement fluid inside the pipe. So gravity makes that heavy cement want to U-tube straight back up inside your casing. To stop that messy flow back, we rely on a tool called a float collar. It's placed down near the bottom of the string. It contains a one-way check valve that lets the cement travel down, but it snaps shut the second you stop pumping to prevent it from coming back up. And crucially, it also provides the machined landing seat for our wiper plugs to land on and create that pressure spike we talked about earlier. Now, cement is highly abrasive, and we're pumping it at high rates. Valves can and definitely do fail under that kind of punishment. Because cement sets only once, we rely heavily on layered barrier logic. We actually run 2 check valves in series, one in the float collar and another one just below it in the float shoe. If one valve gets destroyed by the abrasive cement, the second one holds. That redundancy means a single failure doesn't ruin an unrepeatable job. So what happens if a primary cement job missed a channel, and let's say 10 years later, gas is migrating up behind the casing? The rig's been gone for a decade. You obviously can't dig the well up. You definitely can't rerun the casing. What do you do? This is where we bring in a piece of tech called the cement retainer. It's basically a drillable packer with a one-way controllable valve right in its center bore. It anchors securely into the casing using steel slips and seals up with a rubber element. But because of that center valve, it actually lets you pump new cement down through it and then traps it below. Here's the step-by-step sequence of how we use this to fix an operation known as a squeeze. First, we perforate holes in our own casing right at the leak. We set the retainer just above those holes. We sting or connect a tubing string into the retainer, pump new cement so it's forced out the holes into the void, and then we pull the stinger out. The valve snaps shut, instantly locking the cement in place. You can think of it exactly like a caulking gun equipped with a non-return valve. You're forcing sealant into a crack in a wall at thousands of PSI. But here's the kicker. Cement needs to cure under pressure to fill a void properly. So the retainer's job isn't just to place the cement, it's to keep the pressure on the squeeze long after you've pulled your tools out and headed home. Now, a major hazard to watch out for here is your squeeze pressure. You're trying to fill an existing channel, right? Well, if your squeeze pressure pushes higher than the rock's formation fracture pressure, you're going to accidentally crack the solid rock. Suddenly, all your cement runs off into a brand new fracture that you just made, you've lost the slurry, and worse, you still have the original leak. You might be wondering, why even use the retainer at all? Why not just pump cement down the whole casing? Well, actually scratch that. Doing it without the retainer would mean you'd accidentally fill thousands of feet of your own casing with solid concrete, and you'd have to drill every single foot of it back out. Plus, you wouldn't be able to hold the squeeze pressure the moment you stopped pumping. The retainer localizes the job, meaning you only have to drill out a few feet of tool later on. It really is a high-stakes mechanical ballet happening in the absolute dark. From the cementing head at the surface, launching plugs like a pneumatic tube, all the way down to the float collars catching the fluid miles below, to the retainers fixing leaks decades later. It all comes back to a deeply human question. When the pressure is on and you cannot see the result, how well do you truly trust your numbers when you only get one shot? Think about that next time you assume a machine is just doing the heavy lifting. Thanks for joining me on this explainer, and I'll see you in the next one.